All right, good afternoon, everyone. Apologies for that delay. So raise your hand if you still weren't able to run FreeFem. BT, good? Okay. So it's just now you, Rodrigo, and Stephanie. But then the rest of you are fine? Okay. Well, just let me know if you cannot run it. I'll try to have it installed in geology, okay? But it might be a problem with the version of your operating system. All right, so let's continue then with the lecture. The last thing that we saw was to yes, Jack.
Can we talk about time maybe earlier next week or this content to talk about the exam?
We'll see how we get to that day, but generally graduate class there is no review session.
Maybe not review session, but like what's going to be on the exam.
Oh, everything until the day of the exam.
We won't bring a computer to the exam, right?
No.
But our homework will be done computational, right?
No, you don't have to do any computations, but I expect that you know mostly the theory. Okay? It's going to be mostly theoretical. Everything that you can do, probably you might need a calculator, but I'm most interested in the theory. Okay? So when is the exam? Like 2 weeks from now, right? Okay, we'll have some time till that. I'll check the exam, and I'll give you a few hints. All right? But it's going to be mostly theoretical, with just some small calculations. Okay, you have been working in solving stresses around a cavity with the finite element method and with the Kirch equations. Why do we want to do that? Because that applies directly to wellbore stability. I'm not going to discuss in this class all the details about wellbore stability, but you can go to this chapter number 6, and in here you will find everything you need: the Kirch solution, an explanation of cylindrical coordinates, the solutions for each action, either in a far field stress, a pressure inside the wellbore, or a differential stress around the cavity. All of those are part of the Kirch solution, and you will see all that explained in the notes. With these equations, what we can do is later to check whether there is failure around the wellbore or not. Basically, we compare the stresses that we calculated before with criteria for rock failure. And basically, that's going to be composed by 2 types of rock failure. Shear failure, which is going to give us a failure which is called breakouts. And here you can see all the theory. We'll talk a little bit about this. I'm just going to go very quickly right now. And the next one, which is tensile failure around the wellbore. So shear and tensile failure, both, they can happen in the wellbore, and that's why we are using this solution of stresses, because we want to know whether there is going to be failure around the wellbore or not. And in order to do that, we need to compare stresses in the wellbore with the strength of the rock. Again, everything you will find it summarized in here, and also some design for some guides for wellbore design and for the math of the weight required to avoid failure and some other things that can happen in the wellbore. So all of that is there. So please read it. It's not going to take a long time, but basically it's just calculating the stress around the wellbore, compare that to a failure criterion, and to say whether there is failure or not. Okay? All right. So let me simplify it now in just 10 minutes or less of this entire chapter. And this is what you have to do specifically for the project. But again, please read all that chapter. All right. So with the solutions of stresses around the wellbore, basically what we want to see if there is shear or tensile failure around the wellbore. If this is a wellbore, and let's say I have the maximum stress in this direction, let's assume that this is a vertical wellbore, but you don't have to do that assumption necessarily. Let's say that this is the minimum horizontal stress. All right, so inside the rock we have pores, and there's going to be some pore pressure. And inside the wellbore, there is going to be a certain pressure of the mud in the wellbore. When you solve the Kear's equations, you're going to be able to tell what is the stress everywhere in this domain, either if you do it with finite elements or if you do it with a Kear solution. But what you have to notice is where the failure or where the rock is going to fail around the wellbore and how. So if the maximum stress is applied in this direction, where do you think you're going to have more compression around the wellbore? Let's say that this is the north and this is the east, and we're looking from the top. Do you think the compression is going to be concentrated in the north and south parts of the wellbore or in the east and west parts of the wellbore? And let's think about the hoop stress. The north-south. And why? Because you have your stresses, most of the compressive stresses traveling in this direction. That's a major component. And the minor component is in this direction. So all those stresses have to go around the wellbore. And as they go around the wellbore, in order to make it into the other side, they concentrate in these locations. And as they concentrate in that location, if you look at the hoop stress in these two regions, most of the compression is going to be, or the maximum principal stress, let's talk in the specific terms, is going to be in this direction, and the minimum principal stress will be very likely in this direction. If your maximum principal stress exceeds the shear failure limit, what you're going to have in here is what is called a breakout, and this is a shear failure. We didn't get yet to failure and plasticity, but we'll get to that soon after we talk about poroelasticity. But let me give you a little bit of an advance of this, we'll get shear failures that they look like an X. I don't know if you remember that from the laboratory that we ran here in class. And this region of the rock is going to fall inside the wellbore, and it's going to leave an empty space, and that's what is called a breakout. So let me write it here. North and south locations, we have shear failure for this specific case, and that's called a breakout. And I ran to my office because I wanted to show you this example. This is a cavity similar to the one that you have over there. We apply stress in this direction, and according to what I told you, we should see failure here in north and south locations, okay? So let me look for the right angle so you can see that failure. Okay, do you see that in the back? Probably that's, let me rotate it because this side is better. All right, you see that? Let me zoom in. Okay, that failure that looks like a groove or looks like a scratch inside the wellbore is shear failure. And let me see if I can improve it with light from the back. Okay, so right there. I'm not doing a good job with that. Let me try one more time. Probably it's too much of a zoom. Okay, there. So all of that is failure on the wall of the wellbore, and it's produced by shear. And again, as I told you before, this is because we apply stress in this direction. Most of the compressive stress is going to concentrate on the top and the bottom, and that's a failure that you're going to see. Probably you can also see a little bit of that. It's much clearer when I see it in here, but you don't see very well from there. But let me see the other direction. Okay. So this failure, notice that it goes at an angle, and now we're missing the failure in the other direction if we had a breakout. So in this case, just we have failure going in one direction and not in the other. But is that shear failure? And that's called a breakout. In general, you will look for breakouts checking a criterion of shear. In the project, which is weekly project number 4, the pressure in the wellbore is equal to 0, and you don't have pore pressure. So that's the same as saying that pressure of the wellbore minus pore pressure is equal to 0. And if that's 0, that means that checking for shear is just going to mean that you need to check if sigma theta theta is larger or equal than UCS, where UCS is the unconfined compression strength of the rock. That's going to be the criterion for checking for shear. So unconfined compressive strength would mean that to a piece of rock, let's say like this one, you don't have any stress from the sides, you just compress it, and the point at which it breaks, that's the unconfined compressive strength, and that's exactly the same thing as it happens here. If you don't have any radial support, then you just check for sigma theta theta. If that it's higher than unconfined compressive strength, that means that you have failure in shear. When that pressure support in the wall is not equal to 0, you need to use the full criterion for shear, something we haven't seen yet, but you can see in the notes. It's not too difficult. All right, so we have shear failure. Where are you going to have the lowest hoop stress around the wellbore? East-west, right? If we had in north-south the highest compressive stress for the hoop stress, here you will have the lowest. So in east-west, we're going to have tensile failure. And what is going to be the orientation of those tensile fractures? Are they going to grow in direction east-west, north-south, or at an angle? They're going to be east-west because if we have tension here and here, a tensile fracture is going to be perpendicular to the direction of that stress and is going to open right there. That tensile fracture is what you see right here. Notice the orientation. It's in the same direction of the maximum stress. Let me check the other side. Well, this one, look, had that failure in top and bottom, or east. This would be east and west. So here and there. If you look inside, you see this one propagated a little bit inside, but then it turned, and I think the other one propagated a little bit more inside, and then it turned. But the fracture will tend to be always in the direction, tensile fracture in the direction of the maximum principal stress. For this particular sample, it's cylindrical, and it does not it does not comply with what we're analyzing here, that it should be infinitely long in this direction. So if I had something prismatic, probably I would see this fracture going all the way through the entire wellbore. So how do we check for tensile failure? Basically, what you're going to have to do is this one doesn't depend on the wellbore support. You just need to check that if sigma theta theta is equal or less than the tensile strength. If this is true, then you have tensile failure. And usually for drilling applications, these ones are called drilling induced tensile fractures. And that's everything that you have to check for your project. Sigma theta theta, if it's equal or larger than UCS, then we'll say that there is shear failure. If it is less or equal than the tensile strength, that's going to be a tensile fracture. Later on, after we go through seeing the criteria for failure of rock in under a confined stress, we'll extend this concept to deviated wellbores. Okay, so we'll get back to this later on and apply it to a more general case. Jack.
So tensile failure and tensile fracture is not the same thing?
Tensile failure is just a type of failure of the rock, and the fracture is just a tensile fracture is a type of fractures.
Okay,
So tensile failure leads to tensile fractures.
okay. So that hoop stress is smaller than tensile
Strength. This is tensile strength.
Tensile strain.
Yes.
So what happens here?
You have a tensile fracture.
If it's smaller than the tensile.
Yes, because remember that this value is going to be some number, right? And then your stresses are going to be a negative value. So when the stress is smaller than, well, probably, I think we should add a sign here. The negative, the value of the tensile strength, that's going to be tensile failure. So let's put an example just to make clear. Let's say your tensile strength is 1000 psi. If your stress is lower than negative 1000 psi, that means that that's going to fail under tension. If it's negative 900, that's still okay.
Okay, so I can put it this way: the absolute value of the hook stress must be greater than.
No, you can do that. It has to be negative. It has to be negative. Usually, tensile strength will report as a positive value. That's why I added the negative sign there.
So cannot just do absolute value on both sides.
No, because at some point you can have failure in compression due to compression and shear failure. So where you have compression, positive stresses, check for shear failure. And where you have negative stresses, check for tensile failure. What you could do something like, if sigma is negative, then absolute value of sigma larger than tensile strength, failure. But you could also just simplify that in one line, saying if sigma equal or less than negative tensile strength, tensile failure.
So on a circle in the north-south direction,
Yeah.
the hook stress is positive, and in the east-west direction, the hook stress is negative.
It might be negative. It depends on the value of this, in the value of that,
Yeah.
in the value of these two. But if it is negative, it's going to be here.
Yes.
Rodrigo?
So if you have bigger hoop stress,
Yeah.
I mean increasing hoop stress, what happens to the breakout? Is it growing to the other parts of the well?
Yes,
also?
it's going to start growing.
It's reaching the UCS of the other parts, right?
Well, what is happening in there is that, and there is a good, very nice image in here about that. And where is that? One more. Probably this is a good example. When the rock starts to fail at a point like somewhere over here in the middle, then that rock goes away, and what takes the stress is the rock around it. And if that stress is large enough to fail the rock around it, it starts growing and growing and growing. But there might be a point at which that becomes stable. And at the point at which that becomes stable is what determines what is called the angle of the breakout. And you can also calculate that based on the pressure of the mud and stresses and the orientation of the wellbore and the properties of the rock, UCS, and also the friction coefficient.
But I mean, if you have obviously the same UCS for the rock around the whole wellbore.
Yeah.
And if you have hoop stresses increasing in the wellbore,
Yeah.
it would, I mean, affect, you reach the UCS
Yeah.
around the wellbore in different parts while it's increasing, right? So I don't know, I'm thinking if it would shear along the well in different parts. I mean, if you would have shear in different parts instead of only the north or south.
Well, I think this image answers that question. Hoop stress, here this should be the green is sigma theta theta. It varies according to Kirch's equation sinusoidally. So you have the maximum here and there, but then it starts to decrease, and actually decreases very quickly. as you get away from there. So you will find a point at which the stress, when your breakout angle increases a lot, your stress, hoop stress at that point, say somewhere over here, also is going to decrease. So now it's not going to be as large as it was in the center. And the problem also gets a little bit more complex. It depends on the type of rock and how the rock fails. Some rocks, they get stronger as they go through failure, and some others fail very quickly. That also, the breakout is going to depend on that too. BT? Yeah.
When you test it, the breakouts and the tensile failure happens together.
Not necessarily. No. Yes. Actually, I was thinking about getting one of those samples and filling it here, but I forgot. I'm sorry. If I find a sample, I'll try to bring it, and we'll do it very quickly, so you will see. You can work through the equations, to the Kirsch equations, and if I remember correctly, the tensile failure happens first, but if you keep on loading, the breakout is going to come after. And sometimes we run these examples in the laboratory, and sometimes we don't see the breakouts at all. We just see the tensile failure, and then it just breaks. All right, so this is basically everything that you have to do for project number 4. And again, let me repeat this. Read entirely this chapter number 6, because when we get to deviated wellbores, you're going to need all of these, and you're going to have to solve a harder problem later on. Okay? All right. So let me see if I forget anything. No, I think we're good. Okay, now we're going to talk about the new topic, which is poroelasticity. So far, we didn't talk almost at all about pore pressure, and we'll talk about pore pressure now. For poroelasticity, we're going to follow the material of a book, and if you look at the references, this is the book by Cussy, 2010, chapters 3 and 4. All of you working in reservoir simulation, remember that most of the poroelasticity equations that I have seen in all simulators, they follow the literature from the books from Cussy. They apply straight from that book all of that equations into reservoir simulators. Okay, so poroelasticity is going to be a tool that is going to allow us to predict the formations of rocks, not only based on a variation of porosity, but also based on a strain of the solid. So we're going to consider now that the solid can also be deformed, and not only the pores, but also the solid part. So let's imagine a solid that looks like cheese with holes. This solid is going to be subjected to total stresses, but inside the pores is also going to be subjected to a fluid pressure. And you know, here I'm drawing a pore, but this could also be a fracture. And those pores are going to deform. And this solid may deform too. So the solid is going to deform by the action of stresses and also by the action of the pores. Let me show you an example about where that happens. So let me show you first here. Do you guys know what this is? What it looks? So let me show you the real size. This is the real size, okay? So Jack, what did you say? Marshmallow? No, it's not a marshmallow. Like what? No, no, it's not gauze. No. I'll pass this thing, so you can look at the bottom. This, no. This is a polyester cup. So a polyester cup, like you know, like yeah. So you know those white cups that are usually for drinking coffee, very light. Is one of those, but was subjected to increases of pore pressure all around the cup, so big that it crushed some of the pores inside and just left it like that, deformed like that. So I'm going to pass it around. Please don't break it. That was a gift from a good friend of mine from my PhD. But it was a cup that was probably 2 to 3 times, probably 3 times the size of that. But after applying pressure in all directions, it collapsed and stayed like that. And also you can notice that it looks like a lot more rigid than what it was originally. So all the solid was preserved, but the pores, they collapsed. They got a lot smaller than they were originally. All right, so our porous solid in here is similar to that one. Probably the solid part is not going to be as soft, but it's very similar to that one. And here in this solid, we're going to have pores. In those pores, we're going to have fluids. We're going to have pressure inside the pores. And if we have pressure inside the pores, what kind of stresses can we apply to the pores? Normal only. No shear stress. Because fluids cannot apply shear stresses over a long time. Also, the solid is deformable, so the walls of the pores are also deformable. And we're going to say that the bulk volume of this solid, we're going to call it d omega, and we're going to define a volumetric strain with this equation. Where this one is the initial bulk volume. This thing is, I'm writing it like that because we're going to write a lot of those, and I want to save some space. So that is the same thing as volumetric strain. But I'm just going to write it with one letter, that epsilon, like that. So basically, bulk volume at any time is just 1 plus the volumetric strain times the initial bulk volume. Okay. So we have bulk volume, we have volumetric strain. Let's go step by step. Let's define what porosity is. porosity, let me call it now with letter N. I'm going to say that at the time t, which is not the initial time, the porosity with the letter N is just going to be the volume of the pores up there in the figure, so the empty volume plus the entire volume, which is comprised by the volume of the solids times the volume of the pores.
Can you just say like the space between the grains?
It's well, that's a pore volume, right? But we're making this general because we're not talking about grains. It might be a porous solid, which is made mostly by holes inside of a solid matrix, or it could be a like a foam structure, which it's like full of pores connected by pore walls. So it's not necessarily grains. It's just the empty volume, or the volume that it might be filled by a fluid, divided the total volume, and that total volume is part solid, part empty. All right. When we do this definition, it's very important that we notice that this is the definition of porosity made at time t, and this refers to the bulk volume at a time t. And that's, in math, something which is referred as an Eulerian approach, and because it refers to the current time, and because of that we call this one Eulerian porosity. But in mechanics, if you remember, when we define a strain, we always define it with respect to the original length before deformation at a time equal to 0. That's the way we keep track of strains. It's a change of length divided the original length. So in order to make this porosity theory work for us, we're going to need to work and refer changes of porosity with respect to the original porosity. And in order to get there, we're going to define a new porosity. And that porosity is going to be is going to come from this equation. Porosity at any time times bulk volume at any time, we're going to make that equal to a porosity, a new porosity, porosity phi, times bulk volume at time 0. And therefore, from this equation, this porosity is going to be equal to this. And this porosity is what is called a Lagrangian porosity, because it refers to the initial bulk volume. And this is very important because all the equations that we're going to write make this assumption. All right. So, everything okay so far? Lagrangian. It comes from Lagrange, and it's Lagrangian, I-A-N. All right. So we have bulk volumes. Now we have porosity. There is one more thing that we need in order to be able to derive the equations for the changes of porosity or bulk volume as a function of deformation of the pores and deformation of the solids, and that's going to be the solid strain. So the same way that we have a bulk volume in here, and this refers to that, this is the bulk volume. Also, we're going to have a solid strain. And the solid strain is going to be, we're going to say that the volume of the solid part is going to be equal to 1 plus the volumetric strain of the solid part. Wait a minute. This one, that S goes according to notation of the book, goes down here, plus times the initial volume of the solids. So with equation 1, with equation 2, and with equation 3, we can do some math, which I'm not going to do right now, but you can play with equations. You can do it on your own. If you don't believe the equation I'm going to write, and our objective is going to be to write the volumetric strain as a function of the strain of the solid and as a function of the change in porosity. So this equation, when you combine all of this, is going to be that the total strain is going to be an average of the strain of the solid, volumetric strain of the solid, plus a change in porosity. And just to make this equation more meaningful, I'm going to multiply this times original porosity and divide it times original porosity. So 1, 2, and 3 lead to this equation. And this is an equation that we're going to need in poroelasticity, because poroelasticity, as I told you before, consider changes in porosity as part of the deformation, but also consider changes of the strain of the solid as part of the deformation. In a very soft solid, like for example this one, which is a foam, almost all volumetric strain goes into changes in porosity. So you can see how these layers, they get shorter, and they have less porosity each time I compress it. So all change of volumetric strain goes into change of porosity. However, in rocks, when we get to very high pressures and very high stresses, as we have in the deep subsurface, also the minerals in the rock, they will start to deform when we have such large pressures and stresses. And that's why we have to consider now not only the change of porosity, but the change in the solid part. All right, before I continue with some examples, let's try to understand this equation, because this is very meaningful. First of all, what kind of average, oh no, let me do one thing before. Porosity minus initial porosity, divide the initial porosity. How would you call that? Okay, and we are not doing any percents. We have the option to do that. So do you remember what is the definition of a strain? Strain in general is length minus initial length divided original length. And this looks very similar to that, right? But instead of length, we have porosity. So this term is going to be a porosity strain. And usually the difference in porosity, sometimes we write it just as a letter phi. But don't worry about now. This is a porosity strain. What is this? This is a solid strain. So what kind of average do I have here? For example, when you compute the bulk density of a rock, what do? You add up the weights for each part of the rock, and then you divide that times the total volume of the rock. Or which is the same if you would do with densities, you multiply the density of a given phase times the volumetric fraction of that phase plus the density of the other phase plus the volumetric fraction of that phase, and so on. That's something called a volume average. And look at this. This is also a volume average, a simple volume average. It tells you that the total bulk strain, volumetric, is a volume average of the solid strain, because this is 1 minus porosity, plus the porosity strain times the porosity. So they are weighed, each of these strains, the solid strain and the porosity strain, by their volume fractions, which in this case are these two, this one and that one. So it's just a simple volume average. Yeah.
So, like, do we care about units at all?
Units?
Yeah.
Not here, because strain is unitless. Porosity is also unitless. Forget, we're not using percents here. If we have porosity of 10%, that would be 0.10. So no units so far. Okay, so let's see a few cases that are going to help us understand a little bit more how we can have strains in a porous solid, in a porous deformable solid, which are a combination of solid strain and porosity strain. So we're going to make two cases. Case number one, let's imagine that we have a solid a porous solid in which I apply a pressure inside the pores, and you cannot see here, okay, in this drawing, but these pores are all connected. So any pressure that you apply in one pore, it has to be the same in the other pores. Okay, then I apply pressure P, and in this thaw experiment, we're not going to let the rock deform. So all these triangles mean that there is no deformation. I do not let it deform as I apply the pressure. If this is the case, then from our equation above, that means that the strain, the bulk strain, is going to be 0. And therefore, this is going to be equal to this times that plus the change in porosity, which here I'm just going to write it as, in order to save some space, as a letter phi. And the result of this pressure, if this is an expansion of the pore, is going to tell me that if I expand the porosity, that's going to be at the expense of the formation of the solid. And according to this equation, that has to be equal to the change of porosity divided 1 minus the original porosity.
You're increasing pore pressure?
I'm increasing pore pressure. So if the change in porosity is larger than 0, which means that I'm increasing porosity, what's going to happen with the solid strain? Yes, but let's term, instead of decrease, increase. Is it going to contract or is it going to dilate? It has to contract. And according to these equations, this has to be equal less than 0. Okay, so I wanted to do this because I need to tell you that in order to follow the convention of the book, just for this part, we're going to come back to the mechanics convention in which compression is negative and dilation is positive. So in the mechanics convention, this is a contraction. And in this particular case, we do this because we want to be in agreement with the signs of change of porosity. If the change of porosity is larger than 0, that means an increase of porosity. Okay, but what this example, simple example, shows is that you could have no strain at the macro scale, but you could have inside the rock strains. The pores can get larger and the solid can get smaller, but the overall strain could be 0. Let's see another case. Let's say that I have a similar porous solid. It looks like a smiley face. I have a porous solid and I apply stresses from outside. Remember what we said last class? For any mechanics problem, you either apply stress or displacement. You cannot apply both. So in the previous case, we fixed the displacement on the boundary. Now we're fixing stress on the boundary. Okay, so we apply stress on the boundaries, but then what we're going to do is we're also going to increase the pressure simultaneously as we apply that stress, so that, let's say that I don't have any pressure inside the pores. When I apply stress outside, what's going to happen to the pores? They're going to get smaller, they might crash, if you have enough pressure, but they're going to get smaller. So what we're going to do here is we're going to, as we apply the stress, we're going to apply a pressure which is going to be large enough so that the pores do not deform. We're going to see later on that actually that pressure is going to be equal to the external stress in order to reach that condition. But if I do that and I achieve a condition in which the change in porosity is equal to 0, remember this is that. If the change in porosity is equal to 0 and I use the equation that I had above, that means that what's going to happen to the solid strain? If I apply a compression, yes, it's going to contract, and it's going to be, I wrote that out of here. And the strain of the solid, now in this case, is going to be equal to the bulk strain divided 1 minus porosity. So for example, if I had a porosity, say, of 0.2, and I apply a strain of 10%, because I'm not letting the pores deform, the porosity of the solid is going to be more than 10%. It's going to be 10% divided 0.8, which is how much? I don't know. It's that 12% or so. But it's going to be more. So under this condition, I can have a strain in the solid which is larger than the bulk strain. And that just comes from this equation that we just saw. Okay. Any questions so far? No? So what we have seen so far is how we can relate strains to changes in porosity and strains in the solid. Why? Because we're going to partition now the stress into changes of strain in the solid, which are proportional to the bulk modulus of the solid, and changes in porosity, which, if filled with the fluid, are going to be proportional to the compressibility of a fluid. That's why we need to partition those two. And we're going to use these equations now, and we'll see the application. All right. So we'll just do one more thing today before we start working with those equations. We're going to talk about the energy that can be stored in a porous solid. We are in thermodynamic, people like to call it free energy. But it's just energy in a porous solid. So for example, I compress this foam. I make a work when I compress this foam, and that work goes into stored energy because the foam is compressed, but now as soon as I release the, let me do it more slowly, I release the force, this one expands because the solid is storing energy. While it is compressed, it has stored energy that is going to release it when it suffers a decompression.
How is free energy different from potential
Potential
energies?
energy will be an energy that you stored, for example, when you are at the given position and is independent of the path to which you get. Like for example, raising this rock, it doesn't matter if I do this or that. the potential energy is going to be the same. And this free energy, it's going to be something similar, but it's not related to a position. It's related, in this case, to a strain, or what we're going to add to a pressure. All right, so this solid, forget a moment about the pores now. Just imagine it's a solid, and that it is deformable. Any solid is going to be able to store energy by compression. And because this is a solid, a fluid also can store energy with compression. Like, for example, a gas, you compress a gas, it stores energy. But a solid, in addition, is going to be able to store energy by shear, because solids can bear a shear stress. So we're going to have to add up those two. So far, I didn't talk much about shear, and that's because pore pressure doesn't affect shear. And we're going to see how that comes into equations later on, but now we need to take it into account. The energy then is going to be proportional to a volumetric strain and also to a shear strain. And we can write that as this. Energy is going to be proportional to a bulk strain. And what causes a bulk strain? A mean stress. So the mean stress Sm, where Sm is S11 plus S22 plus S33, that's the one that causes changes in volumetric strain. And the one that causes shear strains is going to be also a shear stress. Okay, let me complete this. This is volumetric strain. And here, similar to this, I'm going to write this shear strain as small e, and I'm going to call it Ij, and here this is going to be lowercase Sij, meaning that this is a shear stress. Ij could be 1, 2, 1, 3, and 2, 3. I'm just writing it Ij here just to be more general. And this one is going to be the shear strain Ij. Remember, we're talking in 3 dimensions. We are simplifying the problem here by partitioning the volumetric strain and the shear strains, but all the time we're talking in 3 dimensions. Okay. Let's add now the porosity. So if I had a porous solid, I'm going to be able to compress it with total stresses. Let's add, just to make it simple, a big pore here in the middle. I'm going to be able to add shear strains to that porous solid. But based on what we just saw before, what other type of strain I can produce in the solid? What's going to be the variable that I need to take into account? So this is bulk strain, this is shear strain, and since I need to consider that the pores are going to deform too, I also need to consider the effect of pressure. So for a porous solid now, this would be non-porous solid. This is going to be a porous solid. I'm going to have this component. I'm going to have this component too. And I'm going to have an additional component, which is going to be depend on pressure. And that's going to be pressure times the change in porosity, where this is equal to also writing that. So we're going to have one additional variable that is going to change the energy that this solid can hold inside. In my example, for example, here I can make a volumetric strain. Probably I can do a shear strain by doing this, but I cannot do a change of pore pressure inside. But if I could do that with a fluid, that would go in this term. Yeah.
dW free energy?
That would be the free energy. Yeah. Yeah, the W comes from work, and that would be the free energy. Okay, I'm not going to derive entirely these equations because that might take a long time, but I want to show where it comes from with one example. And it's going to be, we're going to attack the simpler one, which is this one. Let's say that I have stress here, mean stress, and I have volumetric strain here. And I have a linear elastic material. What is the relationship between mean stress and volumetric strain? Are those linearly related, or with a quadratic function, or with an exponential function for a linear elastic material? Linear, right? It's a linear elastic material, so it's a linear relationship. The bigger the stress, the bigger the strain. Okay, how much work do I need to get to a point somewhere over there, let's say? Do you remember how to work with these plots?
What's the question?
How much work do I need to spend to get to this point? If you have a
Equal to the free energy that
yeah, but we're looking actually for an equation here. If you remember from your Physics 1 class, the work required to get to this point is the area underneath that line. So the work, let's call it dW, is going to be equal to this area. And that area is what? That area is equal to the base of the triangle times the height of the triangle, where the base is just strain, and the height of the triangle, because of the linear relationship, is going to be the bulk modulus times strain, where the slope of this line is the bulk modulus divided by 2. And from here we get that this is equal that to 1/2 of the bulk modulus times volumetric strain squared. That's the work I need to deform this solid. It makes sense that it's proportional to the strain square, and it's also proportional to the stiffness of the rock. The stiffer the rock, the more energy I need to get to the same strain. All right, using this same principle, I can extend the work not only for the variable mean stress, but also for the variable shear stress and for the variable pressure. And actually, we're going to do a small change. Instead of pressure, I'm going to change the variable, and we'll do it in terms of porosity. So this is going to look a little bit different. And instead of W, we're going to call this for the porous solid eta S. And this is going to be the free energy of the porous solid and just of the skeleton part without the fluid, and it's going to be equal to, similar to what we had before, 1/2 K volumetric strain squared plus shear modulus, and that makes sense because any energy containing shear strain should depend on the shear modulus, times the shear strain, and the last term is going to be the term of the porosity and the volumetric strain, and this is going to be, well, actually we have two terms. This is going to be, this is just a constant. Similar, you know, you see this was a constant, K, we knew what that constant was. G, that's also a constant, shear modulus, we know what those are. Where let's say that now this is just a constant. We'll find their meaning later. But it is a constant, and that's proportional to the volumetric strain times pressure. And I'm going to have one more term, which is going to be 1/2 of 1n. And again, this is just another constant. N is just a constant times pressure squared. This is the energy of the solid, considering now pressure. So I have the component of bulk volumetric strain. I have the component of shear strain, and these two capture the component of pressure. Notice that this one captures the influence of both volumetric strain and pressure, and this one pressure by itself. This one is considering explicitly the coupling between volumetric strain and pressure, and this one of pressure just on its own.
And here we're solving for again.
We know what this is, right? We know what K is. We know what shear modulus is. Our objective on Monday is going to be to get to know what alpha and what n are.
What are we solving for again?
For, well, here,
Something S.
yes, we have an equation that tells us what is the energy of a porous solid based on the volumetric strain proportional to a value that we know. That's something that we can vary, like our variables, if you may want to think in variables, are going to be volumetric strain, shear strain linked to a shear modulus, and pressure. where pressure, there's going to be a term that is linked to volumetric strain with a constant alpha, and pressure by itself squared with another constant, which is n. And we write it like this because that's going to be convenient later on. But those are just constants that we don't know yet, and we're going to derive on Monday. Okay, let me see if I forget anything. No, I think that's it. That's it for today. So we'll continue with this on Monday. All right. If you have any questions about the project, again, just let me know. I'm gonna stay in my office till 6:30, 7. So just stop by if you need any help. All right. Oh, okay. Good question, BT. So I know that some of you are still having some issues with this. So today is Wednesday, Monday. Let's say Wednesday. Okay? Let's say Wednesday. All right. Thank you, guys.